Hello, welcome everyone. In this video, my classmates Julia Monar, Marina Suarez and myself, Elena Salvat, are going to present exercise 7.103 from chapter 7, the time-dependent electromagnetic field. First of all, we're going to take a look at each statement. And then, we're going to comment some previous considerations on how to approach this problem. Secondly, we're going to proceed to the resolution of this exercise. And finally, we're going to talk about an alternative case which could be also presented to us. Last but not least, we're gonna comment also the conclusions we extracted from solving this exercise. Okay, so first of all, we're gonna read the statement, which says the following. A coil has an inductance of 53 millihenries and a resistance of 0.35 ohms. An EMF of 12 volts is applied across the coil. Calculate A. Energy stored in the magnetic field after the current has built up to its equilibrium value. And B. The number of time constants that must pass for the energy stored in the magnetic field to reach half the equilibrium value.
The Faraday-Henry law of electromagnetic induction states that the varying magnetic field induces an electromotive force that is equal to the derivative with respect to time of the magnetic flux. A changing magnetic field induces an electric field which, in contrast to the case of electrostatics, it's non-conservative. The minus sign in the previously mentioned law, sometimes referred to as Lenz's law, indicates that the current induced in the loop creates a magnetic field that opposes the change of the externally applied magnetic field. Faraday's law can be proven to apply both when the field changes and the circuit is stationary, when the circuit moves and the field is stationary, or when both change with time, despite these being apparently different situations.
An inductor carrying a variable current produces a change of self-flux, which according to Faraday's law induces an electromotive force, and which is calculated as the minus inductance multiplied by the derivative of intensity with respect to time. The minus sign means that this force opposes its cause. Plus, the energy required to establish an electric current in a self-inductance is calculated with the following formula. 1/2 of L multiplied by intensity to the power of 2. To solve this exercise, we also have to know what is the Kirchhoff's voltage law. It says that in any closed network, the total voltage around the loop is equal to the sum of all the voltage drops with the same loop, which is also equal to 0. Recall that we must consider the polarities and signs of the sources and voltage drops around the loop. Bearing in mind that we have an RL circuit, we have to follow the Kirchhoff's law that we have previously explained, and we must substitute the voltage of the resistance by I multiplied by R with a minus sign, and the voltage of the coil by L multiplied by the derivative of I with respect to time with a minus sign too. After solving the ODE, we obtain that the current in an RL charging circuit is V divided by R multiplied by 1 minus E to the minus T multiplied by R divided by L.
Okay, so this is the data given by the statement, and first of all, we have to take into account that calculating the energy in the magnetic field when I has built up to its equilibrium value is analogous to calculating the energy on a stationary circuit. Therefore, we use the formula of a charging RL circuit with T tending to infinity, which makes the E vanish, and therefore the intensity is equal to voltage over resistance. Then, substituting the variables and the data given by the statement on the magnetic energy expression, we get the following. Therefore, the result is 31 joules.
Constants that must pass for the energy stored to reach half the equilibrium value. First, we write the new energy in terms of the previously calculated one. Then we isolate the current and equal it to the expression obtained after solving the ODE. Then what we do is to calculate which is the value of tau in seconds. Now we isolate the time from the equation that we had before and leave it in terms of tau. Then we substitute with the data and obtain that the time is 1,22 taus. We calculate the equivalent in seconds and obtain that the result is 0,18 seconds.
If instead of a charging RL circuit, we had a discharging RL circuit, this would be initially fully charged and would start discharging. Therefore, the battery doesn't induce any voltage, and only the voltage of the coil and the resistance are taken into account. After solving the Kirchhoff's voltage law, we obtain that intensity is calculated as V divided by R multiplied by e to the minus t divided by tau. Now, since this is the inverse scenario, we will take time equals 0 and follow the exact same procedure. We can find the number of time constants that must pass for the energy stored in the magnetic field to reach half of its equilibrium value, which is 0.35 tau. And we can also find tau and the time and conclude that it takes 0.5 seconds to reduce its energy half of its equilibrium value.
And finally, these are the conclusions we have extracted. First of all, comparing the results obtained in the charging and in the discharging circuits, we can easily see that to reach the energy of half the equilibrium value, it takes more time in the charging RL circuit than in the discharging one.
To verify the results obtained, we have used the units to demonstrate that it is dimensionally correct.
Finally, bear in mind that with the results obtained, it is possible to know the percentage of the total current that has either been charged or discharged in the time for the energy to reach half of its equilibrium value. Substituting time for 1.22 tau and 0.24 tau in the respective equations of current, we obtain that for the charging circuit, it has charged at 70% of its initial current, and for the alternative case, it has discharged at 71%. If you have any questions, be open to ask.